Once again, I want to remind everyone that these videos only have some examples. In general, in Blackboard, there's the section called Textbook Examples, and I'm depending on you to work those examples through them step by step and email me if you're having questions and difficulties understanding. The videos that I've uploaded initially are lecture videos. If I have examples, I'll clearly label those videos as example videos that work through things similar to examples in your text. I'm skipping some sections of the textbook, so sometimes these videos provide insight into little pieces of those sections that I'm skipping. Sometimes in these videos I grab things that maybe you've seen in a previous class, somewhere in K through 12 or something, but hasn't been mentioned recently. In general, I think that people don't read the entire textbook. If you look in a chapter, there's all sorts of words in paragraph form surrounding the examples, and generally I think people skip over that. And I'm not blaming anybody because I do it myself. It's just the way we read textbooks in general. So these videos are trying to make up for that, grab that stuff out. So having said that, let's talk about 6.2 linear equations. First of all, some general rules about equation solving. This would be called basic algebra rules, not to be confused with abstract type algebra, maybe what I do my research in. This is algebra in terms of college algebra stuff. First of all, if you have an equal sign for some sort of an equation, if you do something on one side of that equal sign, you better do it to the other. So you have to keep the balance. There's only one L in balance. I don't know. You have to keep that balance. I think there's two L's. I don't know. I can't spell. I'm a mathematician, people. The other thing, and we've already talked about this one, it's called distribution. Sometimes we go backwards and call it factoring. It's this idea that if I have two things being added together and I'm multiplying both of them, then I have to distribute that A and send it to both the B and to the C. This will be important if, in order to keep the balance in my equation, I want to multiply both sides of the equal sign, and one side of the equals had an addition, then whatever I multiply both sides of that equal sign by, I'm going to have to make sure I distribute to make sure that works. And then I want to point out something about what fractions and whatnot mean. So in math, if I have the phrase 1/2 times x, this is the same thing as x over 2, which may be what sometimes in previous math classes you would have called x divided by 2. In algebra, one of these two formats is the preferred shape for this, which brings me up to my big complaint in life. This textbook does it. Most of your life you've seen things that do this. Let's talk about this. This is my big complaint in life. I have several. This one's about fractions. About fractions. This is half the reason I think that people have such a great innate fear of fractions. It's that we teach it in a horrible way in this country, in our grade school system. Mr. Blitzer, Professor Blitzer, is a wonderful person. He's your textbook author. I love the textbook to pieces. But he and I kind of, I don't want to say disagree, but we have this divergent philosophy here, and he's going with the flow, and sometimes I think flows are meant to be stopped. So here's my complaint about fractions, and here's what I want to point out. In life, we see this number sometimes, and if you saw this in a cooking book, in cooking, you would know exactly, and I said, that it was this many cups of flour. You would tell me exactly what to do. You would give me 4 cups of flour, and then you would give me another ½ cup. You could also call this 4.5 cups. It's the same sort of deal. Sometimes this is used, usually I think in our society this way, but I say that this thing is very risky. It's risky because of this. In math, when you're solving equations, you're all in the business of multiplying things through. And because we use the letter x so much in math, we don't normally write multiplication. So remember this fact. I could write 4x as 4 times x. That's what it means, but this would be a very bad way to write it. So I could also write it as 4.x with that raised dot, not the parenthesis. This is a decimal dot. This is multiplication. And even that's still messy because we tend to write decimals and whatnot in math. So sometimes we just put the two right next to each other like this. If I wanted to be horribly formal about the whole process, I would write it in parentheses like this. This is the only way that there's no possibility of misunderstanding. No possible problems. Here, well, with x there's no problems, but with this 4 times 1/2, because remember x is standing in for something, I might be tempted to write 4 times 1/2 like this. And that would lead me to my big question, am I talking about 4.5? But if I'm writing this 4 times 1/2 to mean multiplication, it technically means 4 times 1/2, which is 4 over 2, which we all know is 2. And this is our big problem. You don't really want to write, I don't know, if I wrote this, maybe that would be clear, but that looks like some kind of weird double decimal fraction thing, who knows what. Again, you don't want to write this. So x is straight out because, maybe I shouldn't cross these out with x's. X is straight out because, let's face it, we have too many x's. This decimal multiplication thing is a little iffy because is it decimal or is it multiplication with the raised dot? I'm a very sloppy writer, as you can see. This is what we usually use in math. This is the fastest. And this is way too complicated. Now, before you despair and say, oh my goodness, I can never learn math. Well, remember, we do this in the English language all the time. The kid had a bat. In general, we would probably assume this means the child has some sort of stick that they're supposed to hit a ball with, but maybe he's got a little cage and has a small flying mammal that we are afraid of sucking our blood at night. So we've got things like the word bat. They look the same. And then we have the phrase like there, and there, which we pronounce exactly the same in this language. They're all spelled differently, but you rely on context if I'm talking to figure out which one of these things you mean. So sometimes we've got words that have multiple definitions. Sometimes we've got words that sound the same that mean different things. So this happens in English too, so you can't go blaming math for this problem. So here's what I want to really mention and emphasize. In this class, I think that writing 4 times 1/2 and meaning it to equal 2 is a perfectly fine thing to do. In the real world, sometimes people write this and they are trying to tell you that they mean 4.5 as a decimal here, 4 cups and then an extra half a cup. Rather than write improper this type of mixed fraction, I think it's called in the book, there's this horrible name for them. They're called improper fractions. But they're actually the best sort of fractions there are. And I think somehow, somewhere in 2nd grade, some teacher decided they didn't like the number on the top numerator to be bigger, and so they called this improper. But this is actually the most proper that it could be, because I can rewrite 4 times 1/2, and I would write that as 4 over 2, and this would equal 2. If I'm trying to convey the idea of 4.5, I can write this as 9/2, because 9/2 equals 4.5. This eliminates this whole confusion process. It's called an improper fraction, but it gets rid of the problem. So my advice to you when you're solving equations is this. Remember that you have to keep the balance of your equal signs, because you're not trying to take an equation that I've told you is equal and make it not equal. You're trying to keep it equal and just solve for x. Remember, if you have to do something like multiply or divide both sides of a fraction or of an equal sign, you're going to have to do this distribution if you've got addition already on one side. Remember that multiplying by the fraction is the same thing as dividing by the denominator of that fraction. And take the time now to write all fractions as improper fractions if you need to. This will save you pain and suffering later on. So, having said that, let me give you an example. And I know I just gave a disclaimer saying I wasn't going to give examples in here. But here's my example. I've got x over 3 plus 1/4 times x equals 1/3. And here's how I solve this sort of thing. First of all, I look at these denominators. And I see that I've got a 3 in one denominator, a 4, and a 3. This tells me that my lowest common denominator here is going to be 12. And so I'm going to solve this equation by getting rid of fractions. In general, I don't like fractions. Even if I've converted them to these nice improper form, I still don't like them in my equations. So here's what I'm going to do. I'm going to get rid of the fractions. I can't just multiply everything by 3 because sometimes there's 4s. I can't multiply everything by 4s because sometimes there's 3s. So instead I multiply by 4 times 3, which is 12. I want to do this to the right side, so I'm going to have to do it to the left side as well. I'm going to do two things here with my little equation. On the one hand, here's what we write. This is the formal math way of getting the job done. On one side, I have x over 3 plus 1/4 x. On the other side, I have 1/3. So far, I haven't changed anything other than groups and parentheses for emphasis. I multiply the right side by 12, and I multiply the left side by 12. When I do that on the left, I have to distribute that 12. And when I do it on the right, I just multiply that 12 through. This gives me some cancellation. 12 over 3 is going to give me 4. 12 over 4 is going to give me 3. There's still the x there. And this 12 divided by 3 is going to give me 4x. 4 plus 3 gives me 7x, because these are like terms. And finally, I divide both sides by 7. Since I divided the left by 7, I had to divide the right by 7. And this gives me x equals 4/7. Perhaps in I don't know, somehow people always think that an answer like 4/7 is bad because it's not a whole number. There's nothing wrong with the answer 4/7. This is a wonderful answer. So this is what we write formally. I take this equation that I'm trying to solve, and I go through this process, and here's how I solve it. However, notice how long this process is. I had 1, 2, 3, 4. There were 5 different things I had to write to get to my final answer. Every time you copy something down, you introduce the chance for a copy error. Here's how I want you to think about this. Remember that 12 is 4 times 3. So really what I'm doing, when I have this 12 hanging out in front here, I really got 4 times 3, this x over 3, plus this 1/4 x, equals 1/3, 12 times 3. Because of that, on the right side here, dividing by 3 and multiplying by 3, dividing by 3 and multiplying by 3 cancel each other out. This leaves me with this side. Oops, not 12 times 3, excuse me, 4 times 3. This leaves me with just a 4 on the right side. Similarly, remember this is going to distribute to both of these. When it distributes to the first one, the 3's are going to cancel, and I'm going to be left with just a 4 getting distributed through. There's still that plus there. When I distribute it to the second one, when you distribute over here to the second one, what's getting canceled? I'm still multiplying the 4 times 3 through. Remember, the 12 went to both of them. But this time it's the 4's that cancel, and that's just going to leave me with a 3x. 4 plus 3 is 7x. Divide both sides by 7 tells me x equals 4 over 7. So this is what you write on the left side. Here's how I want you to think on the right side. Notice I was able to reduce the total number of steps several times. And it also made it less funky. I didn't have this 12 over 4 and then realize that 12 over 4 was 3. I saved time because I remembered, how did I get 12? Well, it was 4 times 3 already, so of course the 12, and once the 4's cancel out, I just have that 3 left. Just have that 3 left. Either way, you get your correct answer. Something to point out about equations and answers, and this is something that your book starts talking about in some of the later examples. Not all equations have solutions. This is because not all equations are true, just like all sentences you speak aren't true. There's 3 possibilities. There's this possibility here where there is one answer, there's one solution. This seems the most common because in a math class we generally prefer to focus on these. But this is actually, if I just randomly start throwing x's and numbers together and equal signs, odds are things actually aren't going to be equal if I just were to randomly create things. So while this seems common, this is actually the least common in the real world. Then there's things that have no solution. You'll be able to recognize these because they'll follow these distinct patterns. So things that have one solution, you know about them. They look like this, x equals 4 over 7. Things that have no solution, you'll go through and solve, and you'll get something that's horribly untrue, like 6 equals 8. This is just not true. This is false. It's horribly false. 6 is not 8, and so that's what tells you there's no solution. That's provided you've done your algebra correctly. Then there's also things that we say have infinite solutions. You'll be able to recognize these because you've done your algebra correctly and you get something that's always true, like 3 equals 3 as your final answer. That means that you can throw in any number for x in the world and it will work. So sometimes you get a specific answer for x, sometimes you find out that x has no possible answers, sometimes you find out it could have infinitely many answers. So then the two last things to focus on in this section in terms of ideas. One is this idea of proportion. Proportion. And it's this idea that if I have a over b equals c over d, this is going to be true if and only if, grabbing from our logic section, a times d equals c times b, maybe b times c. You got this idea that we call cross-multiplying. This is if I have only one fraction on the left and only one fraction on the right. If I have addition like I had up here, this addition right here, that's not true because I don't have one fraction on the left, so I can't cross-multiply if I have more than one fraction on either side. It has to be one fraction and one fraction only. Why does this cross-multiplication process work? Well, maybe if I don't like fractions, I'm going to try to multiply both sides by something. So I have a over b equals c over d. I want to kill off the d, so I multiply the right by d, which means I have to multiply the left side by d. I want to kill off the b, so I multiply both sides by b. Doing my cancellation leaves me with dA equals cb. You know multiplication works both ways, and what that means is that 4 times 3 is the same thing as 3 times 4. They're both 12. So AD and DA is the same, and CB and DC is the same. This is what convinces you that cross-multiplying works. It comes straight out of algebra. It's not something new you have to memorize. It's just some basic algebra that you want to know and understand. So, as we're talking about all of these things, these proportions, these equal signs, what we've been talking about today is something that's called linear equations. There are many types of equations. In the previous section of chapter 5, you've talked about things involving exponents. Linear equations don't have exponents. They look like this: ax plus b equals 0. Another way that you've seen linear equations, maybe in a previous class, y equals mx plus b, and you thought of this y equals mx plus b as being some sort of graph maybe, where this was my line y. This point right here was the point 0b, because this was your y-intercept, and maybe you called this slope. But the idea behind linear equations is that there's just an x, and that x is raised to the first power. There's no x squareds, there's no x cubes, there's just one x, and everything else is numbers. A and b are being numbers here. And the thing about linear equations is that they allow us to model things, model real-world events that have what we call constant change. That have constant change. There is a change happening if you think about this line. As I go further to the right, it gets pushed further up. That's why we call slope rise over run. But the idea of constant change is that while change happens, the change is predictable. The change doesn't change. I don't know, maybe now I'm getting deep and saying, the only thing that ever doesn't change is change itself. But the idea behind constant change is that the change is steady. If you sign up for a job and you know that you get a 4% raise every year, then you know exactly how your income is going to increase. If, on the other hand, you're driving in your car, This is my example of a car. It's got little wheels. The further you push down on that gas pedal, the faster your car's going in terms of speed, which means the quicker your distance is changing. As you go faster, you're able to travel a greater distance in less time. So here in a car, this would be an example of something that's not linear. Whereas if you signed up for this work where you had a 4% raise every year, you put your money in a CD or something that gives you 4%, that would make the change be linear. Linear just means it's able to be modeled by a straight line, kind of coming back to this idea. Again, it doesn't really mention that in the chapter. This is the main idea for the linear equation that you want from this section. So now I think you're ready to look through the examples of 6.2 and maybe some of this stuff in terms of distribution and how fractions work makes this work a little bit better. Remember, improper fractions can be quite helpful because they eliminate this sort of dicey confusion issue.